Welcome to the very first day of a brand new unit, Unit 9. And the title of this unit is kind of a big word, but it's called Reaction Stoichiometry. So that's one of the words in the title here, stoichiometry. And it's a big word, but kind of a really simple concept. And so our goals for today is we want to be able to determine a factor that's called the mole ratio between different compounds and atoms that are involved in the reaction. And then we also want to be able to use that to convert between grams, moles, and molecules of reactants and products. And so to kind of illustrate how this is going to work, I'd like us to do an example with food, kind of first of all. And if you've done any cooking in the kitchen, or maybe at your job, you may work at a restaurant and be in charge of preparing, food or orders, this kind of follows just that same general pathway. So I've got a little reaction here for making a sandwich. And sorry, I was kind of limited on what pictures I could find, so the sandwich isn't too fancy. But it has some lettuce and some Swiss cheese. And so based on our little reaction here, it tells us that we need 2 slices of bread, 1 slice of cheese, 2 leaves of lettuce to give us 1 of our sandwiches, all right? And so if I start out by asking you the first question, how many sandwiches can be made from 24 slices of bread? Most of you all would probably immediately respond, well, 12. Okay. And so then I might proceed to ask you, well, how did you know that so quickly? And so what you would probably tell me then is, well, I knew that each sandwich requires 2 slices of bread. So 24 divided by 2 is 12. Okay. And so what we're going to find is we can take that general concept and kind of set it up in our little fraction system, and it should work out and give us the exact same answers every time. That way, once we move away from sandwich stuff into a little more unfamiliar territory with chemicals, we can just follow the same basic setup. So what we were doing is you were telling me that there were 2 slices of bread required to make 1 sandwich. And so if you remember, anytime that number is in the bottom of our fraction, we're dividing by it. And so 24 divided by 2 is 12 sandwiches, all right? Now, this little kind of ratio here that says 2 pieces of bread produce 1 sandwich, this is going to be what we call the mole ratio, all right? Now here, we're not really dealing in moles, we're just counting with whole numbers. But the idea is this ratio is going to come from the coefficients of the chemical reaction. So it tells us how many of each reactant and how many of each product. Okay, so now let's try just one more sandwich question first. So part B says now how many lettuce leaves should be used? All right. So what we see in this case, if we're still starting with those 24 slices of bread, is for every slice of bread, you also need a leaf of lettuce, because 2 slices of bread to 2 leaves of lettuce. So if we plug that into our ratio, that for every 2 slices of bread, our reaction also tells us that we need 2 leaves of lettuce. Let's see what that works out to be. So I multiply by the top, so that would be 24 times 2. Then I divide by the bottom. And so what that gets me, because times 2 divided by 2 is just 1, I should also need 24 leaves of lettuce, all right? And so that's kind of the idea, is our reactions give us a ratio that can be used to convert between different reactions and different products, okay? So now just kind of a quick little intro paragraph, and then we'll get started with the chemicals. So it says reaction stoichiometry describes the quantitative, so it's dealing with numbers, relationships between reactants and products within a chemical reaction. It is an analysis technique used to determine the amount of products or reactants that are produced or consumed within a reaction. The coefficients of the balanced chemical equation represent relative molar amounts of reactants and products. These are known as mole ratios. All right. So now what we're going to do is we're going to kind of tie all this in with our little framework that we've already learned for converting between grams, moles, and molecules. And so I've kind of brought this back up on the screen again. And so typically, if we simplified this down, you guys were used to seeing grams to moles to molecules, all right? And so the grams, just as a reminder, that's kind of our practical unit for the lab. And the grams are found on the bottom of each element's square on the periodic table. So the elements have a specific number of grams because they each have a specific molar mass. The molecules, that's related to Avogadro's number, which is 6.022 times 10 to the 23rd, and that tells us how many molecules are in a mole. Now, here's where things are going to get a little bit different. Before, does anyone remember kind of what number we always used for the unit moles? Yep, that's it. It was the number 1, all right? Now, here's the reason that is. Before, we hadn't learned about chemical reactions. We were just looking at individual chemicals, say, for example, NaBr. So we just had one substance to work with. But this time, what's going to change is instead of just assuming the number 1 for moles, our moles are going to come from the coefficients of the chemical reaction, all right? So every coefficient represents an amount in moles. Now, the next thing that's going to change is instead of just working with one substance, we're going to be taking a starting substance and kind of comparing it to another substance within the reaction. And so we're going to build kind of a bridge between two of our grams to moles frameworks there. And that's where the mole ratio is going to come into play. And again, this comes from the coefficients of our equation. And so it's going to help us relate two different compounds within the equation. All right, so now what we're going to do is go through and work a few examples, kind of starting at different points on our framework and working to different endpoints. Now, of course, the nice thing is about watching this on video is that if you understand, after watching just one example of the section, then kind of skip ahead in the video a little bit and go to section 2, watch one example there. But if you need a little more help, then you can keep watching because each section kind of has at least 2, if not 3, examples within it. All right, so let's start off with this first example. It says moles of substance 1 going to moles of substance 2. And so I'm going to clear off my little space up here. That way we can track our problems a little more easily. All right, so here we go. So they give us the reaction. We're actually combusting the chemical methane here. And so they ask us how many moles of carbon dioxide can be produced from 3.2 moles of oxygen. So we're starting with some oxygen. We're putting it into the reaction, and we're wanting to know how much carbon dioxide can we get out as a product. So what we're going to do is do a little planning. So oxygen is going to be our substance 1, and carbon dioxide will be our substance 2. So I'll kind of write that in on our framework here. Now it tells me that I'm starting in moles of oxygen. So that kind of puts me right in the middle. Then it tells me that I want to end up at moles of carbon dioxide. So this looks to be a one-step problem that's just going to require me to use the mole ratio, which come from the coefficients. So what we'll do to start our setup is we'll start by writing what we're given, 3.2 moles of oxygen. And again, remember, in your format, it's important to include a number, a unit, and then your chemical symbol. All right. So then, since this conversion will take us one step, we'll set up one kind of fraction area. Then, just like before, whatever unit you start with should be copied to the bottom of the next fraction. Whatever unit you desire to end with should go in the top. In this case, moles of carbon dioxide. Now, what we do is we look at our chemical reaction and we see how many moles of oxygen have to be put in. Oxygen has a coefficient of 2, so that means that the reaction requires 2 moles of oxygen. Carbon dioxide has a coefficient of 1, so that means that only 1 mole of carbon dioxide is produced. All right, so now that I'm in my final unit, I'm ready to go ahead and solve in my calculator. So I'll do 3.2 times 1 divided by 2. And again, the reason I'm dividing by 2 is because it's in the denominator. All right, so now with that in mind, I receive an answer on my calculator of 1.6 moles of carbon dioxide. And again, in your final answer, you'll want to make sure to include your number, your unit, and your symbol. All right. And then just like before, our answer can be only as significant as our starting value. So if we go back and check our starting value 3.2, that had 2 significant figures, which means our answer should be limited to 2, which is 1.6. All right, so let's go ahead and try the we do right quick. Okay, so same reaction, same problem. All right, I'll tell you what, actually, let's skip down to the you do, just because it throws in some different chemicals there. All right, so here we're asked how many moles of methane were used if 4.56 moles of water were produced. All right, so here they kind of give us one of the products as our starting substance 1. So we're going to be starting with water. Clear off my area here. And then they're wanting us to kind of backtrack and figure out how many moles of methane were used. So we're trying to convert from water to methane. We're starting in moles of water, and they want us to end at moles of methane. So this looks to be a one-step problem that will just use the mole ratio from the coefficients. So if we go down, we'll start our setup by writing exactly what we're given. 4.56 moles of H2O. This is a one-step problem. I take my starting unit, moles of water, and copy it to the bottom of the next fraction. I take my ending unit, moles of methane, and copy it on top. Now, if I want to know how many moles of water per moles of methane, I need to go to the coefficients of my chemical reaction. So here it shows me that for every 2 moles of water, I should have used 1 mole of methane. So it's a 2-to-1 ratio. Now I'm ready to solve. So I'll do 4.56 times 1 divided by 2. And that gets me 2.28 moles of CH4. Oops. 2.28 moles of CH4. And again, just to check sig figs, I started with 3 sig figs, which means I should also end with 3. Okay. Now, I'll tell you what, just so it won't take as long to upload, for the ones that don't work in the video, I'll kind of post an answer key for those. That way, if you want to try those and make sure you're good before going on, you can do that on your own, but this way it won't take the video maybe so much time to upload. All right, so now let's go on to example 2, which is where we're going from moles to grams. So we're kind of branching out, and what I want to do is redraw our framework. That way we'll have it handy to use during the problem. So we've got grams to moles to molecules, and that's our substance 1. And then we're going to repeat that setup for substance 2, grams to moles to molecules. And then the bridge, kind of between everything, is our mole ratio in the middle. So that's the one kind of brand new piece to this whole setup. All right, so let's see if we can tackle this problem. So it says, how many grams of rust can be produced from 2.87 moles of oxygen? So oxygen is our starting substance, substance 1. Then rust is our ending substance, substance 2. All right. So for oxygen, I'm starting in moles. And for rust, I'm wanting to end in grams. So based on kind of following my pathway, it looks like going from starting at moles, I'll have to do my first step using the mole ratio. Then I'll be able to do my second step going from moles to grams of rust. So this should work out to be a 2-step problem. So I'll start with what I'm given, 2.87 moles of oxygen. Then I'll set up 2 steps. Just like before, whatever my starting unit is should be copied to the bottom of the next fraction. Okay. So now here we are in our first step. Now this step is special because this is the mole ratio, and it's where we transition from the first substance in moles to the second substance in moles. So we're going from moles of Fe or moles of O2 to moles of Fe2O3. Keep my same color scheme here. And so the mole ratio is the only time that you can change what substance you're working with. Again, where that mole ratio comes into play is from the coefficients of your chemical reaction. My coefficients tell me that I must put in 3 moles of oxygen to get out 2 moles of rust. Now, if I were looking at my framework, I'm now in the unit for moles of rust. And so I'm ready to go from moles of rust to grams of rust. So moles of Fe2O3 to grams of Fe2O3. And so now that I'm on this bottom line, I'm only going to be working with rust. I've kind of left oxygen behind now. So now what it's time for is I need the grams of Fe2O3, which would come from the elements on the periodic table. Now because this is a compound, I'll need to look at iron. It has a mass of 55.85. I'll multiply that by 2. Then I would look at oxygen with a molar mass of 16 and multiply that times 3. When I add those things together, that should give me a total molar mass of 159.70 grams of Fe2O3. Now, here's the catch. Anytime we're using the molar masses from the periodic table, those numbers are defined as being per mole. So when you're doing molar mass, this is where the 1 mole is going to come into play. The mole ratio comes from the equation, but the molar mass is set with a reference point of 1 mole. So it's 159.70 grams of rust per 1 mole. All right, so now let's kind of work through how this would go in our calculator. So we would take 2.87 times 2 divided by 3 times 159.7 divided by 1. All right, and so what that gives us is 305.5593, and it keeps going. So right quick, before we write in our units, let's go ahead and take care of significant figures. So I have 3 significant figures in my starting value. So that means I should have 3 significant figures in the ending value. So instead of 305.55, These are my first three significant figures. The 0.5 would round me up to 306. Then my final units are grams of Fe2O3. All right, and there we go. That's a good amount of rest there. All right. So now we're going to do is let me go ahead and work just one part of each of the other examples. And like I said, I'll post the answer key kind of for the other parts. But feel free, if you wanted this part in the video to kind of pause, and try the you do, then check yourself before moving on. All right. So now let's go to example 3. And again, following the same process, just this time we're starting in grams and kind of working our way to moles. So I'm going to draw in my little setup, grams to moles to molecules, and then finally grams to moles to molecules for substance 2. And again, the bridge between both of these little frameworks is the mole ratio, which comes from the coefficients of the balanced chemical equation. All right, so now let's get started. So this one asks, how many moles of rust can be produced from 6.3 grams of oxygen? They're using the same chemicals, just a little different number. So this time for oxygen, I'm starting in grams, and for iron, I'm wanting to end in moles. So if I track my steps, first, my substance is oxygen. And I'll go from grams to moles of oxygen using molar mass. My second step is to go from moles of oxygen to moles of iron using the mole ratio from the chemical equation. So let's go ahead and set up our problem. So my starting value is 6.3 grams of oxygen. This problem will take me 2 steps, so I'll set up 2 of my fraction steps there. Now I'll go ahead and copy my grams over to the bottom of my next unit. So now I'm ready for step 1, which is where I go from grams of oxygen to moles of oxygen. So I'm still in the same compound. Anytime I need grams, I need to go to the periodic table and look up that element. Oxygen's molar mass is 16, but here I have 2 of them, which gives me a total molar mass of 32 grams per 1 mole. Now, I'm ready for step 2, so I'll go ahead and copy my unit, moles of oxygen, and here at the end of step 2, I'll end up in moles of rust. And so again, the mole ratio is where we make that transition. So let's go to our chemical equation. It looks like we have to put in 3 moles of oxygen to get out 2 moles of rust. We're now in our final unit, so we're ready to solve. So in my calculator, I would plug in 6.3 divided by 32 times 2 divided by 3. And so if we plug in that entire thing there, then we'll talk about kind of rounding to sig figs. So my original answer is 0.13125. But if I look back at my starting value, I only had 2 sig figs there. So I'll need to limit my answer to 2 significant digits. So finally, my answer would be 0.13 moles of Fe2O3. All right, so again, feel free to pause the video and try the you do if you'd like. But if not, we're moving on to example 4. All right, so now here we have a grams to grams problem right quick. So I'm going to recopy my framework. And again, I'd like y'all to kind of practice this because it'll just help you memorize that framework. That way you can have it when you work your problems. Technically, you could just draw one at the top of your paper and use it for every problem. That's totally fine too. All right, mole ratio. Okay, yay, we get a new reaction. Moving on from the rest. Okie doke, here we go. So this one tells us if we're starting with 3.54 grams of sodium sulfide, how many grams of sodium chloride will be produced? So let's go ahead and make our plan. So we're starting with sodium sulfide. Our reaction tells us that's Na2S. And we're ending with sodium chloride, which is NaCl. So we're starting in grams for our first substance and wanting to end with grams for our second substance. So let's plan our steps. So first, I'll go from grams to moles of the first substance. Then I'll go from moles of the first substance to moles of the second substance using the mole ratio. Then finally, I'll go from moles of the second substance to grams of the second substance using its molar mass. Okay. So again, start out by writing what you've been given, 3.54 grams of Na2S. We know this problem will take us 3 steps, so we'll go ahead and set that up. That way we don't leave out a step later. I'll copy my unit to the bottom, grams of sodium sulfide. Then in step 1, I'm keeping that same compound. I'm just transitioning to moles. And the reason I have to go to moles first is because I eventually have to use the mole ratio. And if you've noticed, on each of these problems, the mole ratio has been used every single time. So that's why if we don't start out in moles, we have to get to moles first. That way we're ready to use the mole ratio. All right. So again, I need my grams of Na2S. So I go to my periodic table. I look up sodium. I multiply its mass by 2. I add up sulfur with that as well. And I get a total of 78.04 grams of Na2S. And again, since that's molar mass, that's always per 1 mole. Now, I've completed step 1 and I'm ready for step 2, which is the mole ratio. So I take my unit and copy it to the bottom of the next fraction, moles of Na2S. Now, because this is the mole ratio, I'm ready to change my compound and go to moles of NaCl. The ratio for these compounds is found in the chemical equation. So it tells me I should produce 2 moles of NaCl for every 1 mole of Na2S that I put in. Now that I'm in moles of my second substance, I'm ready to reconvert to grams, which is my final unit. So moles of NaCl to grams of NaCl. Again, this is molar mass, which is always defined as per 1. So I take sodium's mass, 22.99, and add it to chlorine, 35.45, and that gets me 58.44 grams of NaCl. Then we're ready to plug in and solve. It's a good calculator practice here. So we'll do 3.54 times 1 divided by 78.04 times 2 divided by 1 times 58.44 divided by 1. So on my calculator, I'm seeing 5.3018. Now in my starting value, I only had 3 significant figures, which means that I should limit my answer to just 3 significant figures. So 5.30, the 1 makes me stay the same. So my final answer will be 5.30 grams of NaCl. Pencil that in there. All right. So now we've kind of worked almost all the ways you can do this little graph, except for the last one because we haven't touched the molecules area yet. So let's go down to example 5 right quick and check out one of the molecule problems, and then we'll call this lesson a wrap. Okay, so let's get our framework copied just one more time. Grams, moles, molecules. Grams, moles, molecules. And the bridge that connects them is the mole ratio. Okay, substance 1 on top, substance 2 on bottom. All right, let's do this. So we've got our setup, and it says how many molecules of hydrochloric acid are needed to react with 0.234 grams of sodium sulfide. So we're starting with sodium sulfide, Na2S, and they're asking us to convert to hydrochloric acid, HCl. All right, so let's go ahead and make our plan here. So I'm starting with grams of sodium sulfide. Again, that's a more practical unit for the lab. And I'm asked to convert to molecules of HCl. So let's make a plan. So because I need to use the mole ratio, my first step will be to convert from grams to moles of Na2S. Then I can use the mole ratio to go from moles of Na2S to moles of HCl. Finally, I'll go from moles of HCl to molecules of HCl. Again, my molecules are kind of looking at it from the tiny perspective. All right, so let's get started. So I'll start with my 0.234 grams of sodium sulfide, and I'll go ahead and set up 3 steps. All right, so now I copy my starting unit to the bottom of the next fraction, and I'll look at my framework to see what my first step is. My first step is to go from grams to moles. And again, I'm still using that first substance. So I'll look and add up its molar mass, which we already found to be 78.04 grams per 1 mole. Now I'm ready for step 2, which is using the mole ratio. So I can swap compounds and go from moles of Na2S to moles of HCl. The mole ratio comes from the balanced chemical equation. That tells me that for every 2 moles of HCl, I also need 1 mole of Na2S. Finally, for step 3, I'm ready to go from moles of HCl to molecules of HCl. Okay, and again, when we're using molecules, this is where Avogadro's number comes into play, which tells us that there are 6.022 times 10 to the 23rd molecules in 1 mole. So both molar mass and Avogadro's number are defined as being per 1 mole. And so again, if you will, definitely make sure you've got your calculator on this one to make sure you're doing your scientific notation correctly. So you'd start off and type in 0.234 times 1 divided by 78.04 times 2 divided by 1 times 6.022 times 10 to the 23rd divided by 1. And what that gets us for an answer, it's kind of a big long number, 3.6113 times 10 to the 21st. So let's round some sig figs here. So remember, leading zeros are not significant. So I only have 3 significant figures here, the 2, 3, and 4. So I'll need just 3 significant figures, the 3.61. The 1 tells me to round down, in other words, stay the same. So my final answer will be 3.61. Oops, let me not forget the times 10 to the 21st. That's important. Molecules of HCl. All right, and there you go. So again, if you were maybe a little fuzzy as we were going through, take the time to stop and try some of the other examples and check with the key before moving on to the practice problems. Other than that, thank you. I know this lesson was a little longer and I appreciate y'all hanging in there. Great job.